Welcome back. This is the day the Lord has made. Let us rejoice and be glad in it. In this video, I'm going to talk about reaction mechanisms and reaction coordinate diagrams. In a nutshell, these things talk about how the chemical reaction actually takes place. So, as an analogy, you can think of it like you going to school. How did you get to school? So you start at your house, that's the reactant. You at your house, the product is you at school. How do you get there? That's what we're going to be talking about. So we would propose mechanisms for how we think you get there, because again, kind of like we're not watching you come to the school, just like we're not watching individual molecules and what they're doing too along the way as well. Oftentimes with bazillions of atoms, we don't know what's going on. We just know that somehow these things rearrange themselves into this thing. Oftentimes too, we ignore these things along the way, this process. For example, you eat sugar, you burn sugar, it turns into CO2, turns into water. Does it all happen instantaneously? Does all of a sudden, you look at the balance equation, 6 oxygens simultaneously come into contact with one sugar molecule, and then boom, everyone immediately just separates and turns into what they're supposed to be, the carbon dioxide's in the water. What more likely happens is it's a slow process where like an oxygen might hit it and then pull off a carbon or hydrogen, and then slowly the molecule gets taken apart. All right. The reaction mechanism talks about all those individual steps along the way. Back to our analogy of like, well, how did you get to the school? Did you take 4th Street? Did you take Ida? Did you take 168? Did you take 156? What road were you on? Did you zigzag through some neighborhoods? We don't know. The balance reaction doesn't tell us how you actually get from point A to point B. It just says this is what we get. Now, for reaction mechanisms, we try to figure out what they do and how they work, and we look for things along the way. So if we were watching, trying to find how you did this, we could put people at different intersections and say, did we see you come along here? In the chemistry world, it'd be kind of like saying, well, along the way, we think we saw this molecule at some point. So maybe it's along the way. All right, so anyway, reaction mechanisms talk about the whole process of how does it actually change from this chemical to that chemical. So there's a couple things to be aware of for this. You should be aware about things like catalysts and intermediates. So catalysts, they are not a reactant and they're not a product. They wouldn't show up in the balanced equation. They're just something that helps it out, which means that they usually show up, they're part of this reaction mechanism, but they're not part of the balanced equation. So they're helpful for the reaction taking place. You can think of it like a tutor helping get your homework done. You have unfinished homework, then you have finished homework. The tutor is a catalyst. They don't put their name on your homework you're turning in. They help you get it done faster, though. They help you learn the stuff, and so they're not part of the balanced equations. It's your unfinished homework, your finished homework. They're a catalyst. They're there to help you. Intermediates, as another thing to be aware of, intermediates are things you produce along the way, but they're not part of the balanced equation either. So this might be better to think about like writing a paper. So when you're writing a paper, you start off with a rough draft, and then your rough draft becomes a second version, and then you have a third version and a fourth version, and finally get to your final draft. The rough draft and the second version, third version, those are all considered intermediates. They're not the final product, and they weren't there to start either. In fact, it's more like the start is like an idea. You have an idea, turns into a paper, a rough draft turns into a final draft. The rough drafts along the way, those are intermediates. They're not actually part of their overall reaction. So we call those other small steps, I should mention real quick, elementary reactions. Individual steps along the way. They're an elementary step. So every single time you have a big project, you take all these little tiny steps to get there. And so you do a small piece here or there. And so even like writing a paper, the elementary steps include different parts of the paper. Like maybe you spend a day working on the bibliography. Maybe you spend a day working on the footnotes. Maybe you spend a day working on X part of the paper, okay? So generally think about chemical reactions and reaction mechanisms. We generally say that you should never have more than 2 things reacting. So probability just says that you're not likely to have more than 2 molecules come in contact with the right orientation and right energy to react at that moment, which is why, again, back to the idea of like reacting with sugar, 6 oxygens reacting with 1 sugar molecule simultaneously, not going to happen. This could be like along the way, we're going to have an oxygen show up, another oxygen show up, and they're going to keep one at a time showing up, not everyone at once. So, all that's a little bit of backstory for this stuff here. So let's go ahead and talk about catalyst, intermediates, and what the actual overall reaction. So I'm going to be looking at the right side here. So we would propose reaction mechanisms. A reaction mechanism that's being proposed says we think this is what happened, which would be kind of like a step-by-step, this happens, then this happens. All right, so here we have a proposed mechanism for how we actually get ozone to turn into oxygen. All right, so we see that step one proposed that maybe a chlorine reacts with an O3, and this turns into ClO and O2, and then the ClO continues to react and reacts with another ozone to turn into, oh, sorry, let me zoomed in, pulled out, there we go. So then the ClO reacts with the ozone, another ozone, to make Cl plus O2. So a catalyst is something that's going to help us start the reaction off. They don't get used up, they're not part of the balanced equation. We see that we have Cl here on the reactant side, and in step 2 later, we have Cl again on the product side. Something that shows up first as a reactant and comes back out later as a product is a catalyst. It's not going to be part of the balanced equation. It helps us get started and then comes out again at the end. Kind of like your tutor. The tutor helps you and then leaves. The tutor is not consumed in the process. And so intermediates, this will not show up on the balanced equation because we didn't actually use it up. It's when you're buying catalysts for a chemical reaction as an industry, you don't need to keep replacing it. It just keeps working. All right, like you have a catalyst in your car engine that helps turn the smog back into nitrogen and oxygen. You don't need to replace that catalyst. It just keeps on working. There's also intermediates. Intermediates are things that we produce and then consume. So here in step 1, in the first step, we produced ClO, and then we used it again in a later step. So an intermediate, something we produce on the product side and then consume later as the reactant side. This would be like in the paper analogy, you write a rough draft, and then you take the rough draft and you make more modifications and you get the final draft. And so the rough draft, that intermediate doesn't show up in the balanced equation either. So here I've just highlighted what they are. So the catalyst is the Cl, because it starts as a reactant, comes out as a product. The intermediate is ClO, because it starts as a product and comes out as a reactant. To find the actual equation then, what actually is happening, you add the stuff up on the left side, add the stuff up on the right side, and boom, this would be the actual balanced equation. This is saying that, hey, 2 ozones turn into 3 oxygens. So again, big idea here is we would see that, hey, our atmosphere's ozone is being depleted and it's being turned into oxygen. And the question scientists ask is, how is this happening? And they propose, well, maybe I think it's this happening. They say, well, I think the chlorine is reacting with the ozone up there. And then the chlorine, when it reacts with the ozone, turns into this molecule, which keeps reacting. So this is the process by which these things turn into this. All right, let's do a sample together. So here we're given a mechanism, and we want to find out what the actual overall reaction is and identify the catalyst and intermediate. So here we have a step, and we have another step, 2-step process. So if we see something on both sides, if it's as a reactant and a product, it's going to cancel out. So let's actually answer for the catalyst first. So a catalyst would be something that shows up first as a reactant, comes out as a product. So over here, we see the NO starts off as a reactant, and later on, it comes back out as a product. That means that the catalyst here would be NO. He is going to be our catalyst in this reaction mechanism. He's not going to be part of the balanced equation because when we add it up, it cancels out. An intermediate is something we produce and then use. In step 1, we produce NO2, and then we use them again in step 2, which makes this guy the intermediate that we're generating along the way. Now, if it's not one of these guys, it'll be part of the balanced equation. So we add these things up, this would be O3 plus O goes to make 2 O2s. This would be another example of how maybe the ozone is being depleted. The only difference, sorry, it's on the wrong side there. Okay. I don't know what's on the wrong side there. Oh well. Anyway, this would be the reactant. These are the 2 things that are actually going to be left over, and our product is 2 O2s. So we'll get pretty much the same reaction as the last one. We end up taking ozone and turn it into oxygen, but it's through a different mechanism. This one used chlorine as a catalyst. This one is using nitrogen monoxide as a catalyst. All right, you'll see up here too, I wrote a slow step and a fast step. In every reaction mechanism, we can think of it like some steps are fast, some steps are slow. The slow step we consider to be the rate determining step. When you think about the rate determining step, I want you to think about the thing that really holds you back, the thing that slows it down the most. What's going to take the longest? So maybe an analogy is you're going out to eat. So you and your family decide to go out to eat, and you got to decide what you want to eat. And well, before that, you got to decide where you want to go even, you know. So there's a lot of steps along the way. So where do you want to go? Well, you have to wait for the food to be cooked. Will your waiter be fast to bring out the food? Maybe the waiter doesn't give you the check at the end. One needs to be the thing that's to be the slowest step, and it'll determine how long it takes. All right. If you already know what you want to eat, that might be a real fast step if you've been to the restaurant before. But if you've never been there before, it might be the slow step. And so the rate determining step will be the thing that dictates the rate at which the reaction actually takes place. Now, in real life analogies, it might be close. It might be like, okay, the time it takes for the food to be cooked takes about as long as it takes for me to actually think about what I want to buy, what I'm going to get. In chemistry, it's usually not close. Usually there's one step that's super slow and the rest of the stuff is super fast. And so when you think about speeding up a reaction, you want to speed up the slow step, not the fast step. You know, as a teacher, you know, what takes longer, to print off sheets for my students to work on or to make the sheets? All right. If someone came and said, hey, we want to sell you a new photocopier, your old photocopier makes 100 sheets a minute, this one does 200 sheets a minute. Is that going to help me out a lot? Not really. I'm not really spending a lot of time waiting for my paper to come off of the photocopier. You know, in fact, I just click print from my desk and I wait a few minutes, and when I think it's done, I go show up and pick it up. All right. You know, having a faster photocopier is not going to get my work done any faster. So it'd be a waste of my time to speed up an already fast step. All right. The slow step is making the actual material. That's a slow step. If there's a way to speed that up, that would be helpful. You can also think in terms of like being a business manager. You know, think about your people coming through. What is the slowest part of the process for whatever you're doing? All right. Whatever the slowest part is, that's where you want to put your catalyst on. You want to help that part out. You don't need to speed up fast steps. You need to speed up the slow step. Okay. So maybe an example would be like, you're running McDonald's. You are now the manager of McDonald's. Congratulations. All right. So you want to make sure that when people come to McDonald's, they get the food as fast as possible. And so you got to make sure you know how many people to have for every single thing. Whichever thing is the slowest part of the process, you need to have more people doing that. If the slow part of the process is placing the order, you need to have more cash register people working there. If the slow part is actually cooking the food, you need to have more people cooking in the back, more chefs. Again, only you would know at your situation what's going on, but it doesn't make sense to speed up a fast step. You need to speed up the slow step to have any impact on the reaction, okay? So rate determining step, that's the one that determines how fast it is. The future you, when you're in charge of your own businesses, you need to make sure that you put your energy towards making the slow steps faster. And the fast steps, it doesn't really help you a lot if you put your energy into making them faster. It's not really helping you out the most. All right, another word to be aware of here is activation energy. Activation energy is connected to rate determining step. It's related to all these things. It's related to how much energy does it take for the chemicals to rearrange themselves. How hard is this step? These things, rate determining step and activation energy, go hand in hand. Whichever one is the rate determining step is also the one with the largest activation energy. It's the toughest thing to do. So when you think about like another analogy, be a cross-country race. You know, on a cross-country course, you have a lot of hills you got to run up. And you can think about each hill having its own activation energy, like how much motivation, how much energy does it take to get over this hill? And so one of those hills will be the rate determining step. It's gonna be the one that dictates who wins and who loses. So if you get to the cross-country course and you see like there's about 5 or 6 hills and the 6th hill is like, you know, 3 or 4 times higher than the rest and twice as steep, you're looking at the hill and like, that's gonna be the one that dictates who wins this race. Whoever gets up that hill first is gonna win. Whoever's able to conquer that hill the fastest wins. It also has the highest activation energy because it's the biggest hill. All right. So big ideas from this first few minutes here. A reaction mechanism is just a way to describe how things go from the reactant side to the product side. And we propose mechanisms with elementary steps, which means like small steps along the way. How do we get there in small steps? Catalyst, start the reaction off, come out the end. Intermediate is produced and then consumed. The overall reaction, just add them up together to find out what it is. Whichever one is the slowest step will be the rate determining step, which also has the most energy it takes to do that one. Okay, we'll talk about that more later through talking about reaction coordinate diagrams. A reaction coordinate diagram basically takes that idea of the chemicals reacting and puts them onto an energy diagram and saying, okay, here's what's actually happening. All right, and on this reaction coordinate diagram, we're going to have hills for every single step along the way. Okay, so we're going to have our initial reactants turning into our products, and then we're going to have all these elementary steps along the way getting there. The size of the hill will dictate how much energy it takes to get over that and how fast it is. So looking at this one here, to complete our first step, it's a really big hill. This would be considered our slow step, which would be the rate determining step. This one, the hill isn't quite as tall, so it's a faster step. They have their own individual activation energies along the way. So this is kind of like that, connecting to the first analogy, the first chemical equation we had. Maybe the chlorine reacts with the ozone, and this first step is hard to do. All right. And then the next one's faster. And so also to take note on this here, this is a potential energy on energy on the left side here on the y-axis. Here's the reaction going forward. If the hill goes up, that's endothermic. So we should mention that every hill always goes up to start because back to first semester, anytime you break a bond, takes energy. So here, what are we doing? We're breaking apart the ozone. So that's going to take some energy. You've got to break the ozone apart. Think about going up here, taking it apart, and then making a new thing. It's like I'm taking these Lego sets, I'm going to pull them all apart, and then I'm going to make something new. So as we come back down, this is the new bonds forming. So the actual overall step, since we still finished higher than we started, this is an endothermic step. The second step, as given here, is exothermic. We spend some energy, and then we come down further. So since we finished lower than where we started after the hill, that's exothermic. So this would be classified as an exothermic step. This is an endothermic step. The overall reaction, though, finishes higher, so that's endothermic. So again, endothermic finishes higher. Exothermic finishes lower on the energy diagram. And if we compare the speed of these reactions here, this is a slow step. It could be a long time for a person to run up this hill and get to here. And so this would be very fast. So again, think about cross country. Here's course 1, here's course 2, and this is the height elevation. Times for this one here look like they're about 25 minutes for the winner. This one here looks like the person winning is about 15 minutes, maybe even less than that. So, all right, let's connect this to catalysts then. Catalysts, they don't change the actual overall change energy, they just make it easier to get there. So you can think about catalysts just like bulldozing the top of the hill and be like, here's an alternative path. It'd be kind of like, okay, I know all the rest of the cross-country runners are running over the hill, but how about you just go through this tunnel here and ignore that hill? That's what a catalyst does. It just speeds up the reaction. So here's another example. This one actually has 3 steps along the way. Answer some questions about this thing here. This would be a very, very slow step. This first step is endothermic, and it's the biggest hill, so this would be the rate determining step. If we want to get this done faster, we got to speed this one up. The next step is pretty fast, and it's exothermic. The third step is slow, not as slow as this one, but it's still relatively fast compared to that. So we'd have 2 fast steps and 1 slow step. This one here is endothermic. The overall reaction is endothermic. So let's connect this thing here to this sample question down here. So one last one to look at. So here's our reaction. HBr, hydrobromic acid, reacts with oxygen to make water and bromines. And here we have a proposed set of 3 steps. Again, 3 steps, each step is a hill. So connect this to the top. We have a slow step, fast and fast. This would be the first step. This would be the second step. This would be the third step. Identify the intermediates. Intermediates are things that we're going to produce and then we're going to consume. So we see in the first step we make Huber. All right. So, and then we use Huber in the second step. So that's going to be here, going to be classified as, let's pick a color for that. It's obvious. There we go. There's intermediate. So another intermediate, we have HOBr and another HOBr. Both these guys here are going to be intermediates because what happens, we produce them on the product side and then consume them. You'll notice that this one does not have a catalyst because there is nothing that shows up on both sides. HBr, HBr, two more HBRs, that adds up to 4. We have an oxygen, so nothing else is being canceled out. This has no catalyst as given. It says we find a catalyst to help out step 3. How does this affect the rate of the reaction? Again, we got to remind ourselves that speeding up a fast step does not help at all. You might be tempted to say, if I can speed this hill up, it'll help. Sure, you can make an argument for that, but in this class here, my picture diagram does not do justice to the difference. In chemistry, generally the difference between the fast step and the slow step is huge. So this first step, now if it was drawn to scale, let's assume this first step here is Mount Everest. So step 1, climb over Mount Everest. Step 2, climb up the hill at between 4th Street and Ida. All right, this is really fast. So if I make this step faster, it does not make a single difference. All right. So if you're not putting a catalyst on the slow step, has no change. So catalyst step 2, no change. Catalyst step 3, no change. Catalyst step 1, big change. You're gonna make it faster. Which step has the greatest activation energy? The slow step. Step 1. Step 1's gonna have the biggest activation energy. It's the hardest to get over. How many bumps on the diagram? As mentioned, we have 3 steps. Each step gets a bump. Step 1, step 2, step 3. All right, God's peace.